Okay, the next two concepts we want to look at are velocity and speed. Now, a lot of people would use these two terms interchangeably. They don't really understand that there's a difference between them. And sometimes you can actually get away with that. Sometimes, because they are very similar terms, you can sort of use one or the other. But there are other times when you absolutely have to know what the definition of each one is, because there are subtle differences that lead to very different results. And so, in order for you to be able to work problems, you have to know what these definitions mean. So pay close attention to these definitions and examples, because I think they'll bring that point home. Okay, in a previous video we talked about displacement, and we said that displacement was the straight line vector from some initial position to some final position. So we might go on any kind of weird path from the starting point to the ending point, but the straight vector from where you start to where you end up, that's your displacement. But here's the thing. I could go along this displacement slowly, I could go along it quickly, I could go slow, speed up, or start quick and slow down. I can go in a long, circuitous path, I could go in a straight path. There are an infinite number of ways that I could go from my starting point to my ending point. And each of those times could take a different amount of time to get from where you start to where you end up. And so we can talk about the rate of motion, or the rate at which position changes, and that is just going to be the displacement divided by the amount of time it takes to go through that displacement. So that's the rate at which the position is changing, and this is what we will call the average velocity. Okay, so we have this definition that we want to make here for average velocity, and it's simply the change in position, or the displacement, divided by the change in time. So delta r over delta t, where r is our position vector. So again, it's either change in position or displacement. It's not change in displacement. That's something that my students sometimes will put on a test that doesn't mean anything. So don't put that down if I ask you for the definition of average velocity. What I want is either displacement over time or change in position over time. And that's what this delta r is. That is the change in position. So again, the average velocity vector is defined as the displacement vector divided by the time interval over which the motion takes place. And remember that displacement is another way of saying change in position. Now, we talked previously about the difference between displacement, which would be represented by this green vector here, and the length of some path. So if this black curve represents my path from A to B, and it could talk about the length along that path. Well, if I'm going from A to B in a car, say along a curving road, I could measure the displacement and divide it by the amount of time, but that would be a little bit different from what you would probably think of if you wanted to know about the rate at which you were going, how fast you were going. And so we actually have another definition that is distinct from average velocity, and that is the definition of average speed. And so, whereas average velocity was the displacement vector divided by the time, the speed, the average speed, is the distance, or the length of the path traveled divided by the time. And since length or distance are scalars, then we can say that speed is a scalar. And that's our first really big difference between speed and velocity. So the first thing is we've got the definition of velocity, which is the displacement vector divided by the time, and we have the definition of speed, which is the distance divided by the time. So the definitions are fundamentally different, but what really is the big distinction between the two is that displacement is a vector and speed, or distance rather, is a scalar. That means also that speed is going to be a scalar. Now, if we want to talk about the units, because every physical quantity has units, and if I'm talking about position, displacement, distance, these are all going to have units of some kind of distance, like a meter, a foot, a mile, a kilometer, something like that. If we want to talk about speed and velocity, they actually have the same type of unit, and it's going to be some length unit divided by some time unit. Now, if you talk about something called dimensional analysis, where you break things down into their most fundamental units, you would write that the dimensions of velocity are length and then time to the -1 power. That should be to the -1 power there. Um, in the SI convention, that is the metric system that is typically used in math and science, velocity and speed generally will have units of meters per second. But as I mentioned, other common units are also available. So let's just summarize again because these definitions are so important. Average velocity is defined as the displacement vector divided by the time. Average speed is defined as the distance traveled divided by the time. Now, here is a useful note that we'll talk about more as we go. We've already said the magnitude of the displacement vector is a distance. And so the length from there to there, if I were traveling, rather than traveling on this curved path, if I were to travel along a straight path from A to B, I could measure that distance, and that would be equal to the magnitude of this displacement vector. The magnitude of the average velocity vector similarly is going to be a speed. And so if I take this displacement vector and divide it by the time, I'm going to have a velocity which has a magnitude. And that magnitude corresponds to the speed going along the straight path. And so that really gives us a second idea of how to use the concept of speed. And we'll talk about those more as we go, but I just wanted to point that out because these are important ideas, and I want you to see them again and again so that they hopefully have a chance to stick. So here's an example, and you can think about this for a minute. The question is, a runner completes one lap on a circular track with a radius of 50 meters in 42 seconds. What is her average velocity? And so I start here, or the girl starts here rather, and she goes around this circular track, and she makes one complete lap, and it takes 42 seconds for her to do that. So what's the average velocity? The answer should be easily forthcoming to you. The average velocity is going to be equal to 0 meters per second. And if we were being really anal, we would say that's the zero vector because we know it's got to be a vector. But it's got to be 0. Why does it have to be 0? That seems a little bit unintuitive because this person is traveling over this distance and it takes some time to get there. So how is it that the average velocity is 0? Well, think about what the definition of velocity is, of average velocity. The definition of average velocity is displacement over time. We can say that the definition of average velocity gives us that the average velocity is equal to the change in position over the change in time. So far, so good, but now let's think about it. What's the change in position? She starts here, she goes all the way around, she ends up right back where she started, she completes one full lap, her change in position is 0. That means that this term, this delta r, is 0, and anything multiplied by 0 is equal to 0. So the average velocity works out to be 0 meters per second. And that would be the answer to this question. It's kind of a trick question, but it's useful for illustrating the point because, again, the definition of velocity is very different from the definition of speed. So what would the average speed be then? We'll consider this part B of our example. What is her average speed? And the definition of speed is just distance over time. So we need to figure out what's the distance in going around the circle. So she starts here, she goes all the way around. What's that distance? Well, that's obviously just going to be the circumference of the circle. So if we look at this, we know that the circumference of the circle is given by the formula 2 pi times the radius. And so the distance is going to be 2 times 3.14 times 50 meters, and that would be 314 meters. The time is 42 seconds, that was given on the previous screen. So we simply divide the distance by the time, and we end up with 7.5 meters per second. Now, is that a reasonable number or not? I don't know. How might we check that out? Well, we can kind of imagine this by looking at some other ideas. So a typical marathon, if you run marathons or you know someone that runs marathons, typical marathon is 26 miles in length, roughly, or about 42 kilometers. And most people that run them typically run them in 4 to 5 hours. But an elite runner, someone who's like really does marathons like crazy, they can generally do it in about 2 hours. So you can imagine that an elite runner is going to be going about 13 miles per hour or about 5 meters per second. So, I mean, that is a speed that is sustained over 26 miles. So it does maybe seem reasonable that a good runner could maintain a speed of 7.5 meters per second over a 300-meter sprint. You know, we said it was 314 meters, about 300 meters. It seems like it might be within the realm of possibility. It might be a little bit off, but it's at least not an unreasonable answer. And that's something that I want you to cultivate as a habit. It's very important for you to always think about your answers and just ask yourself the question, does this answer make sense? Because sometimes you're not going to be able to tell. If I give you a problem and I ask you to calculate the mass of an electron, you may have no idea what the mass of the electron is. And I mean, you're going to know it's something really small, but is it 10 to the minus 15, 10 to the minus 25? If I gave you answers with those values, you might have no idea whether that was good or bad. And in fact, if you didn't Google the answer or look it up in a textbook, you might have no idea. So sometimes you just don't know if your answer makes sense or not. You just have to go with what the math tells you. But if I give you a problem to calculate the mass of a bowling ball and you tell me that the bowling ball has a mass of 50,000 kilograms, that might be an indication that you made a mistake somewhere because that's not a reasonable answer. And maybe you did a conversion wrong or something, but or maybe you typed something wrong in your calculator, who knows, but just by thinking about your answer, you can catch mistakes. But if you just say, oh, the calculator said it was 50,000, so I'm going to write that down, you're going to look a little silly doing that. So think about your answers and check and see if they make sense. And let me just give you a idea that's worth thinking about also. On a test, when I grade my tests, if you get an answer that doesn't make sense, and you point out that you recognize that the answer does not make sense, you maybe can't figure out what you did wrong, but you say, I'm thinking about my answer, and there's no way that it's 50,000 kilograms because it's a freaking bowling ball, and that doesn't make any sense. I will give you so much more partial credit than if you just leave a wrong answer. Okay, so always work to think about your answers, get into that habit, and on a test, if the answer seems to be awry, let me know that you realize that you're thinking about it, that you're doing the important work of thinking about your answers. And I promise that I will reward you for that because I think it's such an important skill to cultivate.